In this video, we solve problem 6.3.9 from Nagle's Fundamentals of Differential Equations, 7th edition. We're asked to find a general solution to the given differential equation. And notice that we have a linear, third order, non-homogeneous differential equation. It's non-homogeneous because all the y's are on the left-hand side, y and y's derivatives, and all the terms involving the independent variable only are on the right-hand side. And after we do that, the right-hand side is non-zero, so that makes it non-homogeneous. And then we have constant coefficients over here on the left. Since the right-hand side is a constant times an exponential function, we can use the method of undetermined coefficients. Remember, the method of undetermined coefficients only applies when the terms on the left-hand side, after it's been rearranged so that it looks like this, where all the y's are on this side and all the functions of the independent variable are on the other. If these all have constant coefficients, and they do, we've got a 1, a 6, a 12, and an 8 as the coefficients of y, y prime, y double prime, and y triple prime. And then the right-hand side has to be either a finite sum or product of exponential functions, sine or cosine functions, or polynomial functions, or of course just one of those without being a sum or a product. Just a single term would be fine as well. So the method of undetermined coefficients applies here, and that means we're seeking a general solution of the form y equals y sub c plus y sub p, and y sub c is the solution to the corresponding homogeneous problem. So the first thing we do, in order to have the correct form of our guess for y sub p, is to solve the corresponding homogeneous problem. So we just set the right-hand side equal to 0. And then we solve this using the appropriate method. Since this is a homogeneous linear equation with constant coefficients, we're going to let y equal e to the mx. And since it's a third order equation, we need to compute y prime, y double prime, and y triple prime. So we'll have m e to the mx as our first derivative, and then the second derivative gives us another factor of m, because the derivative of e to some power is e to that power times the derivative of the inside. The derivative of a constant times x is just the constant, so the constant comes out every time we take a derivative. Take the derivative again, we're going to multiply by another m, so we'll have an m cubed there. Now we're assuming that y equals e to the mx satisfies this equation. So that means if y equals e to the mx satisfies that equation, we should be able to substitute all of this into the equation, and the equation would still be true. So after substitution, the equation becomes this. We've got y triple prime plus 6 times y double prime, which is that m squared e to the mx, plus 12 times y prime, which is m e to the mx, plus 8 times y, which is e to the mx, and that's equal to 0. So if y equals e to the mx satisfies this equation, then this equation must be true. That will be the case if the following is true. I would factor out e to the mx here. So another way of stating that equation is in this form. So we have this times this equals 0. The only way that equals 0 is if one of the factors equals 0, but e to the mx is never 0. So we get this polynomial must be 0. So e to the mx will be a solution to the differential equation as long as m satisfies this polynomial equation. This is called the characteristic equation of our DE. Now, if it factors easily, you always want to just factor it. But I'm looking at it, it doesn't look like it factors easily. Factoring by grouping is not going to get me to the answer simply. So I think I'm going to have to do something else. If factoring by grouping doesn't work, I always go to possible rational roots as a starting point to try to find at least one root of the equation, the polynomial. And if we have one root of this polynomial on the left-hand side, that's enough to get us a factor. And once we have one factor, we can divide it out to find other factors. So let's list the possible rational roots of a polynomial equation. Those are values of m of one of the following forms. The possible rational roots are given by the factors of the constant term, in this case 8, divided by the factors of the leading coefficient. And that's an implied 1. Factors of 8 include plus and minus 1 and plus and minus 8, plus and minus 2 and plus and minus 4. And the factors of the leading coefficient are just plus and minus 1. So we actually have a list of 8 possibilities. So 1, 2, 4, and 8 could be our possible rational roots, or -1, -2, -4, and -8. Now, first of all, I know I can narrow this down even more. These are all the possible rational roots of this polynomial equation. I'm looking for values of m that will cause this to be 0. Notice that all coefficients on this list are positive. We've got a 1, a 6, a 12, and an 8. So if m is a positive number, this is going to be a sum of positive numbers, and there's no way we're getting 0. So m can't be positive. Those are out. So that narrows it down quite a bit more. Now the question becomes, if this polynomial has a possible rational root, now it's got to be one of these. And if so, which one is it? Or if the polynomial has a rational root, excuse me, it has to be one of these. Which one is it? So you can just guess, pick a value of m and see if it gives you the right thing. I think m equals -1 probably won't work, because we would have 4 or 6 and 8 is 14, and then a -1 and a -12. So -13 and 14 will not work. So I'm going to skip m equals -1 because I've kind of done that one in my head and I don't think it will work. Now try m equals -2. This one is a little bit harder to do in my head, so I'll write out my work on the paper here. I'm going to take -2 and cube it, add 6 times -2 squared, add 12 times -2 plus 8. We're just doing arithmetic. Remember, square that first and then multiply by the 6. And that's nice. We've got the positive 24 and the -24 and the -8 and the positive 8. So these guys reduce and these guys reduce. So that means we get 0. Very nice. So m equals -2 is a root of the polynomial. And remember what we learned in pre-calculus. If m equals -2 is a root of a polynomial, then m plus 2, that's m minus this value, is a factor of that polynomial. So that means that the original polynomial, m cubed plus 6m squared plus 12m plus 8, can be written as m plus 2 times some polynomial over here. Now, this is cubic, and we're saying it's this cubic polynomial is the product of a linear polynomial and another one. In order to make this times this a cubic polynomial, this q of m would have to be quadratic. I actually did not use q of m for quadratic. I used the q for quotient. So this polynomial is equal to m plus 2 times q, where q is the quotient of this and this. And we know, again, it's going to divide evenly because we know that m equals -2 is a factor. Now we just have to find q, and the easiest way to do that, I think, is to use synthetic division. So let's see, what did we do? We listed the possible rational roots. We try values of m until we find one. let's say we find a root of the polynomial. And once we do that, you want to write your polynomial this way. And so now we need to find q. So we're going to find our polynomial q using synthetic division. All right. So we had this guy. Actually, let me look at that again. Oops, sorry. 6m squared, 12m, and an 8. And we want to divide it by m plus 2. In order to do that synthetic division, we're going to set this equal to 0 and solve for m. It gives us m equals -2. It's just the root that corresponds to that factor being 0. We already knew that that factor was 0 when m equals -2. That goes in the little box over here. And then the coefficients of the polynomial in the numerator go here. We need all the powers of m in descending powers of m. If there are missing powers of we need to add placeholders. But there are no missing powers of m. We've got an m cubed term, an m squared term, and m to the first, and then the constant term m to the 0. So that's fine. That's in the right order. So we'll just list the coefficients of 1, 6, 12, and 8. There's an implied 1 in front of that m cubed. Then we bring the 1 down. And synthetic division works pretty easily. You just multiply these guys together. It's -2, and then add. Multiply gives me -8. Put that there, then add. Multiply gives me -8, and then add. And this would always be the remainder. When you take this polynomial and you divide by this, you're going to get some quotient plus a remainder divided by the original divisor, m plus 2. But because m equals -2 is a root, and we already knew that it was a root, we get a 0 here, and you should get that every time. So that means that this divided by this is a quadratic polynomial, and that quadratic polynomial has these coefficients. Since it's quadratic, it starts with a constant times m squared. So this tells me that q of m is 1 times m squared plus 4 times m plus 4. And that our original polynomial, the polynomial on the left-hand side of our characteristic equation, can be written as m plus 2 times m squared plus 4m plus 4. And remember, we're trying to factor this because we're setting it equal to 0. So I'm almost ignoring that now, and I'm thinking about this quadratic and how it factors. It actually factors to m plus 2 times m plus 2. I've got two numbers that multiply to give me 4 that add to 4. 2 and 2 will work. And it turns out that we have 3 factors of m plus 2 there. So we've got a repeated root and m plus 2 cubed. So we get 3 m values because it was a cubic polynomial, but they're all the same. m1, m2, and m3 all turn out to be -2. So we did the synthetic division. Then we factored the characteristic equation as much as possible. And then we find the values of m. There are 3 of them. And then next we need to find the 3 linearly independent solutions, or 3 just in general linearly independent solutions of the original differential equation. So we'll have y1 equals e to the m1x. y2 looks just like it because these are repeated roots, but then we multiply by an extra x. And y3 looks just like it, but we multiply by an extra x again. So remember what these are. These are functions that satisfy this differential equation. So e to the negative 2x, if you plug that in here, you're going to get 0. X times e to the negative 2x, if you take its derivative 3 times and you substitute, everything's going to cancel and you're going to get 0. And x squared times e to the negative 2x will also work and you'll get 0. So those are all 3 solutions to the corresponding homogeneous problem. And remember what we said when we talked about our preliminary theory. If we take each of these and multiply them by constants, they're still solutions to the homogeneous problem. And then if we take each of those and we multiply them by constants and add them together, that sum is a solution to the homogeneous problem. So we use these to come up with 3 solutions to the homogeneous problem: C1, Y1, C2, Y2, and C3, Y3. And then we add them together. But remember, this is a solution, this is a solution, and this is a solution to the homogeneous problem. And then this is a solution to the homogeneous problem. This one is too, and this one is too. And if you don't remember that, you might want to go back to the preliminary theory videos for higher order differential equations. Okay, so that's how that works, and that's how we interpret this. It's third order, so we have 3 solutions, and it looks just like that. All right, now we want to go back to the original differential equation. Y triple prime plus 6y double prime plus 12y prime plus 8y equals, and the right-hand side is now 3 times e to the negative 2x. All right. So first, when we're using the method of undetermined coefficients, we look at the right-hand side and we use that to guess the form of y sub p. Since this is a constant times e to the negative 2x, my initial guess would be that constant times e to the negative 2x. But remember what we just talked about. I only want to use this as my guess if it's not on this list of 3 expressions, 3 functions that all satisfy the corresponding homogeneous equation. Now I know it looks different, but it's really the same thing. This is saying y sub p is a constant times e to the negative 2x. But a constant times e to the negative 2x would cause all of this to equal 0, not this. So we can't use this. So we'll multiply by an extra x, and our hope is that this is not on this list. But it actually is. We already have a constant times x times e to the negative 2x on that list. So we say, okay, probably shouldn't do that. We say, okay, what do we do from there? Well, multiply by x again. And then you say, is that on the list? Actually, it is. We've got a constant times x squared times e to the negative 2x. So multiply by 1 more x until you've got an x cubed. There is no x cubed times e to the negative 2x on that list. So this is going to be the right guess, or probably will be the right guess. Sometimes you might even have to go to x to the 4th, even if that one's not on the list. It happens infrequently. Most of the time, this is going to be just the right guess because it's not on the list, but it has the right form. So we state the educated guess for y sub p. For y sub p. And we're assuming this is a solution to this equation. So we'll take the derivative a few times, and then we'll substitute it in. We'll set the result equal to this, and that should give us an equation involving a and this guy, this 3 over here, and we can solve for a. So let's compute the first derivative. Now I'm thinking of this as a product of 2 functions. That's my first function. That's my second function. According to the product rule, the derivative of this product is the derivative of the first times the second, and then we'll add the derivative of the second. Derivative of e to the negative 2x is e to the negative 2x times the derivative of the inside. It's derivative of the second times the first. Oops, there we go. Now this is not simplified, so we'll simplify it from here. I would factor out the e to the negative 2x. So you have 3ax squared here, negative 2 times a times x cubed there. That's your y sub p prime. And now we want to find y sub p double prime. Here's our first function, and there's our second function. We'll get derivative of the first. Just by the power rule, that's that. Times the second. Plus the derivative of the second. It's e to the negative 2x times the derivative of the inside, which is negative 2, times the first. And we can simplify that as factoring out the e to the negative 2x, we have 6ax minus 6ax squared. Over here we have a negative 2 times 3ax squared is another negative 6ax squared. And then the negative 2 times the negative 2ax cubed is going to give me a positive 4ax cubed times the exponential. And of course these two terms can be combined to give us a negative 12ax squared. Okay, so I just rewrote all of that so that we could keep going and we could see everything that we were doing as we compute the third derivative. It was a third order equation, so we need the third derivative. Again, we'll use the product rule. This is our first function, that's our second. We'll do the derivative of the first. Derivative of a constant times x is just the constant. Then over here, we're going to use the power rule. We have the constant times 2. In this case, it's going to be a 24a, negative 24a, times x to the 1 less power. It's going to give me an x to the first. Then we're adding this constant times 3, which gives me a 12a, times x to the 1 less power. So that's going to give me an x squared. So we have that polynomial times e to the negative 2x, and then we're adding the derivative of the second. So this is derivative of the first times the second, plus derivative of the second. Derivative of e to the negative 2x is e to that power times the derivative of the inside. And that's going to be multiplied by the first function. Undifferentiated. So we're just computing y triple prime here. And we want to factor. We want to make this nice and clean and easy to add together, because we're going to add all of those together on the left-hand side and set it equal to the right-hand side. So factoring out the e to the negative 2x, I have this polynomial, so I'll just write it down. And then we have negative 2 times this polynomial. Negative 2 times that will give me negative 12ax. Negative 2 times negative 12ax squared is going to give me a positive 24ax squared. Negative 2 times this is negative 8ax cubed. And all of that is multiplied by e to the negative 2x. And then we want to simplify wherever we can. Can we simplify anywhere? Let's see. I've got a constant term, that's the 6a, so it's still there. I'm going to check these off as I go. Then I have x terms. I've got a negative 24ax minus 12ax. That's going to be negative 36ax. 12ax squared plus 24ax squared is 36ax squared. And then we have minus 8 times a times x cubed. And that entire polynomial is multiplied by the exponential. Okay, so now we've got all of our y sub p's, potential y sub p's, because this is a guess. We're trying this. To figure out if this guess works, we need to substitute y sub p prime, double prime, and triple prime into this differential equation. Now, if we were to do that all in line, it would be a lot. It would be difficult to keep track of everything. So what I recommend we do is we just do something that we did in arithmetic. Back in elementary school, we often had flashcards that looked like this. We were adding vertically. We're going to add vertically here as well, because it just makes the bookkeeping a little bit easier. And we're assuming y sub p is a solution to this equation, so we're substituting y sub p, or this form of y sub p, in here. Or potential form of y sub p in there. So we have y sub p triple prime plus 6 times y sub p double prime plus 12 times y sub p prime plus 8 times y sub p. And we want to collect like terms in columns. So first with y sub p triple prime, I'm just going to rewrite that right here. Then I want to add 6 times y sub p double prime. Y sub p double prime is right here. I'm putting that in a box to make it a little bit easier to see. We want 6 times this, so we're going to multiply every term in the polynomial by 6. So that's going to be a plus 36ax. And I'll line that up with the other x term here. And 6 times 12 is negative, or the negative 12 is negative 72. So we'll have negative 72ax squared. And 6 times 4 is 24. So we'll have 24a x cubed times the exponential. Okay. That's y sub p double prime. And here's y sub p prime. We want 12 times that. 12 times 3ax squared is going to give me a 36ax squared. Lining it up with the other x squared terms. And then we have 12 times the negative 2ax cubed. That's going to give me negative 24ax cubed. We're adding that. And of course, it's multiplied by the e to the negative 2x. And then finally, for the last one, we want 8 times y sub p, and y sub p is that expression right there. So I want 8ax cubed times e to the negative 2x. Now, because I have lined everything up in columns like this, kind of like we did over here, remember, it's going to make it very easy to see what cancels and what doesn't cancel. Notice we've got a negative 36ax and a positive 36ax. So those are gone. 36 plus 36 is 72. And we're subtracting 72 of those, so those are gone. Got a negative 8a there and a positive 8a there. Negative 24 and a positive 24, so those are gone. So the only thing that's left is the 6a times the exponential. Everything else canceled. So that's the left-hand side of that equation. We want to set that equal to the right-hand side, and the right-hand side was 3 times e to the negative 2x. Isn't that nice? Now, the only way these two polynomials are equal, or excuse me, polynomials, the only way these two expressions are equal is if the coefficients are equal, because you've got a constant times e to the negative 2x on this side, and that equals a constant times e to the negative 2x on that side. So the 6a must be equal to the 3. Okay. So before we go on, we came up with an appropriate guess y sub p by first looking at the right-hand side and then multiplying by x as many times as necessary so that our guess y sub p was not on this list. This has an x, that has an x squared, this one has an x cubed. So when we multiply by x cubed, it's no longer on the list. We took the derivative 3 times because it was third order, and then we substituted into the differential equation, and the substitution step happened right there. Of course, we simplify and we set the result on the left-hand side equal to the result on the right-hand side. And then you have an equation for the only unknown, the only undetermined coefficient a. So 6a is equal to 3. We'll solve for a, we get a equals 3 over 6, or 1/2. So that means y sub p is a, which is 1/2, times x cubed times e to the negative 2x. So we find our a value, and we substitute a into the form of y sub p. And then after we do that, we state the general solution. We know that y is equal to y sub c plus y sub p. And y sub c was c1 e to the negative 2x plus c2 x e to the negative 2x plus c3 x squared e to the negative 2x. And then we're going to add our y sub p, which happens to be 1/2 x cubed times e to the negative 2x. And this will work for all real numbers. So it's always good to state our interval of existence as well.